Hello, hello. Welcome to today's webinar. We'll be talking about some cool stuff around the kernel in AI. Right. So while we let people roll in, I did have kind of a icebreaker question. How many of you in the audience have experienced pain around kills, out of memory kills in Kubernetes? If you have, feel free to drop your trauma, your PTSD into the chat, or just raise your hand and add yourself to the collection of people who've struggled with that. We'll talk a little bit about that today. Give it a couple minutes, maybe one or two, and then we'll just get started. Go ahead and share my screen. Get that all ready. Yeah. Right. Oh, I forgot to update my slides already. It is not March 2026. It's August. Thanks for the heart for people who have been in that situation before. All right, so let's just go ahead and let's get started. So today we are going to be discussing a topic that's pretty near and dear to my heart. Um, I call it kernel observability. So what the heck does that actually mean? So you're probably already familiar with observability, right? You have observability for a given application. You can be able to, start pulling in metrics and understand the behavior of that application. You might want to know how it's performing. You might want to know, how much resources it's using, et cetera. If you're on the kind of platform engineering side, you have observability around your platform, right? Like you understand exactly how much compute you have at any given point, how much, compute is being used across which workloads, et cetera. If you're on the security side, there's also security observability. So you might be running something like an eBPF agent. You might be identifying some type of, attacker behavior and being able to detect that so that you can, follow through and, further lock down your environment or do some incident response should something go wrong. But what we're talking about today is actually something that's specific to the kernel. We'll kind of dive into what that actually means and why this is actually crucial, not just for cloud native, but also in the new world of, AI and AI agents and all of our new, intelligent overlords. So as kind of referenced here, there's a lot of focus and emphasis on AI agents recently, right? So like AI agents are effectively kind of becoming the new workload. There's already a huge amount of work in the community to get AI agents to run in prod. And if you mean, running in prod, that's pretty much synonymous with running it on Kubernetes, right? So there's a lot of effort to basically run AI agents in Kubernetes as pods, of course, and have all of the kind of benefits that you get by running workloads in Kubernetes. All of the kind of auto scaling and all of the kind of self-healing capabilities that Kubernetes provides, batteries included. We want those for our AI agents. So at this point, we're basically going to be discussing what it's like running these AI agents, both from a security but also from an operations perspective. So first off, let's go ahead and talk about the elephant in the room. There's been a lot of really interesting news happening in the world of AI agents. If you've been living under a rock for the last couple of days or maybe a week, just a quick catch up. So there's been the most recent incident or the most kind of salient incident was there was a OpenAI agent or a set of agents. One of them was unreleased, as far as I know, and then one of them was just a standard agent. And this agent actually was basically running with, dangerously skip permissions enabled. The idea is that this was a new unpublished agent or model. And this model was, this job was to basically see how good it was at exploitation. AI agents or AI models are really good for vulnerability discovery. So, you can point an agent at a code base or a running application, and it's really good at being able to identify vulnerabilities. But the kind of crucial and more complicated aspect of that is, can those vulnerabilities be exploited? That introduces a whole different set of challenges. So, unlike just identifying a vulnerability based on looking at some code, understanding whether you can exploit that vulnerability comes down to, more difficult aspects like the runtime environment, right? So like, for example, if you have address space layout randomization, which is kind of like a memory protection mechanism enabled, can the agent actually go from a vulnerability to being able to take advantage of that vulnerability and exploit it, to do, something like, get remote code execution or take over a machine. So this OpenAI agent was effectively being tested, given that it's a new model, um, in terms of how good is it at exploiting software. And as part of that, it was going through a benchmark called Exploit Gym, which is actually a really interesting set of exploitation properties. If you read the white paper, it's really fascinating. There's three different types of exploitation that they focus on. One is user space, one is the kernel, because the Linux kernel is obviously very, critical. And then the other one is basically, V8 isolates, which is what Chrome uses for its sandboxing. So the idea here is like, can you exploit these given, runtimes? And this OpenAI agent was basically going through this set of benchmarks to see how good is it at exploiting, these components. And it kind of identified that maybe the best way to get the best score on this benchmark isn't to, actually go through and rigorously go through each test and exploit each of the systems, but rather it was going to it decided the best, path forward was to cheat on the test. It was to basically just get the answers and get a perfect score. Shouldn't be too surprising if you've ever, had similar thoughts in high school. Of course, I never did. But that's what the AI agent decided to do. So in this case, the AI agent was explicitly aimed at exploiting software, which means that OpenAI had removed all of the kind of like safety mechanisms for the model. So if you've ever run Claude and you've asked it to do something that Claude basically, confuses as being a cybersecurity job that it's not willing to do with Mythos, it'll kind of, revert back to an older model of Opus. And all of those protections were turned off in this OpenAI model. And what that means is that it can basically, hack at will, and nothing is going to stop it. There's no safety mechanisms in place to, provide any safety. So what it ended up doing is it basically decided that it was going to break out of its sandbox, as it's known. Now, this is kind of a fancy new term, but the idea is that it was confined to this environment. It didn't have default internet access. It was restricted only to a Artifactory instance, and that Artifactory instance basically could serve packages for it. So, instead of being able to arbitrarily talk to the internet and pull in, whatever software, it could talk to this local package repository and pull down any software that it needed to be able to achieve its objective of exploiting software. Now, what it did is it found a zero-day vulnerability in that Artifactory system. I think it actually found two vulnerabilities. One agent found one and then left a note. I think it was the latest that I read. And then another agent found another O-day vulnerability. It basically achieved remote code execution in the Artifactory's environment and then broke out of its sandbox. So it's really crucial that we start thinking about, these autonomous systems. Like how do we effectively, run these things safely? Um, and that's one of the things that we're really focused on here at Edera is running untrusted code. And we kind of believe that, AI agents are pretty much synonymous with untrusted code. It has access to be able to install packages and talk to the internet and be able to exploit software. So we very much consider that to be untrusted. So we want to keep those things contained and confined within their own environment. So we effectively want to be able to do that in prod, and then that's basically the bread and butter of Edera. We run containers, which is what this exploit gem benchmark does for user space applications. Is it runs inside of a container and it basically tries to break, out of that environment. It tries to exploit the software that's inside of that container. We run containers inside of microVMs. So instead of a standard container that runs with a shared kernel, what Edera does is we run that container inside of something called a microVM, which is a virtual machine with its own dedicated kernel. So even if that AI agent goes rogue and it decides to exploit the software that's running in the container, it is confined to that container. You can't go from, that container, for example, in this case, to the Artifactory instance or to another environment through lateral movement. So that's what we do. We basically are a very highly secure, untrusted code execution environment for containers. But today we're kind of talking about observability. Now, these two things are actually complementary to each other. And how is that? Well, if you've ever thought about hypervisors, and you probably haven't. But if you ever have, you probably think about them in terms of isolation. Like, how do we, isolate one container from the other? And that's very much, you know, something that a lot of folks on the platform engineering side think through. So how do I, run a bunch of different tenants? They might be running a bunch of different types of code. Maybe some of them is really sensitive. Maybe some of them are kind of throwaway. Maybe we know that some of them are running known vulnerable versions of a container image, etc. How do I keep all of these tenants from basically, taking over the entire cluster, right? Like if I have one tenant with a set of highly valuable cloud credentials on it, and I have on the same node a tenant that's running a extremely vulnerable version of Apache Spark. How do I keep those credentials safe, knowing that I'm running something in a multi-tenant environment? So that's kind of the platform engineering perspective. But if you're a developer, why would you care about isolation? Why would you care about hypervisors, right? Like you probably don't. In fact, when you run a container in Edera, which will kind of show what that looks like, you don't even really know that you're running inside of a micro VM. It looks just like a container. There's really no difference. It's kind of invisible to the developer. Um, but I was kind of wondering, like, what if it wasn't? What if we could enable developers on the Edera platform to be able to, get the benefits of isolation in addition to, just standard containers. So let's go ahead and show you what that looks like, using an example, right? So basically what we're going to do is we're going to run this example workload, which I already launched in the background, which is we're going to run Claude CLI or the Claude Code rather. And we basically, run it inside of a container. You can see this command line here. We're running kubectl exec. We're basically telling this, Claude Code observed to run with, dangerously skip permissions. So it's not going to stop and ask for permission for anything. And we're basically going to say, go find an O day in one of the most battle-hardened pieces of code out there, which is the Go standard library. So, we in this case we want to find, vulnerability. We want to, get maybe a bug bounty or at least, some type of recognition. And it's going to go off and it's going to do its thing, right? So we can't really predict how it's going to achieve this. So just like the situation where the OpenAI agent decided to not go through each test and vigorously try to exploit each, piece of software. It decided that the best thing that it was, the best way to achieve this was to basically cheat and then find the exploit gem answers. We can't guarantee that this job is going to be safe in our environment. Of course, we explicitly stated dangerously skip permissions, but we also are saying, we don't know how it's going to achieve this. It might decide that the best way to do this is to compromise our local production environment and break out of its environment. We just don't know. Um, Now, the crucial thing is that if you think about this from a developer or from a platform engineering perspective, agents are not microservices, right? So, Kubernetes was built for standard microservices, and AI agents look very different from microservices if you're running them inside of Kubernetes, and you have to really know what the differences are because they're quite crucial to understand. So let's kind of talk a little bit about how they differ here. So in the case of standard microservices, we're going to kind of focus on memory because memory is obviously a hugely important topic in applications, and in this case, there's no exception to that. So in this case, memory is proportional to load, which basically means that if you have a web server and that web server is handling, you know, 35 connections, then theoretically it's probably going to be, spawning 35 threads to handle those connections, right? And as that load grows, that it's going to, we're going to have, proportional memory. Each, new inbound connection gets a thread. We're going to have a proportional load to that. We're all very familiar with this pattern. In AI agents, it's very different. Memory consumption is actually kind of wildly separate. So, in the case of an AI agent, it's all about that context window, right? So if you've ever chatted with, Claude or OpenAI or whatever, and as you keep on, as the tool is given a set of, a directive, and then tool goes out and, maybe forks off some processes, and then, slowly builds towards achieving that objective. That context window continually grows, right? It never kind of scales down to zero. It just keeps on, growing as the context window, keeps getting more complicated. Um, Now, in standard Kubernetes, workloads are short-lived. So, I can't remember what the average lifetime of a container is, but it's not really that long. I think it's, in some cases in the minutes. In the case of AI agents, it's completely non-deterministic, just like AI is in general. This means that you can have an agent that runs for, minutes, just like a standard ephemeral workload, or it could run for hours or even days. And the crucial aspect of this is that, with microservices, they're typically stateless. There is a lot of state. I mean, state is kind of the whole thing with an AI agent. That state is completely irreplaceable, and that means that if this workload goes down, then all of the work in that context window is gone. Um, so in the case of standard workloads, if you think about kills, which are basically like, this application has used too much memory, and the, Kubernetes system is going to kill it because it's, consuming way too many resources. Typically, these are like stateless replicas, right? Like you can just kill a given process and restart it. And if it's handling, for example, that inbound, web service request, it just spins up a new thread and everyone's happy. In the case of an AI agent, a kill is completely not recoverable. You might have, for example, 35 minutes of work that the agent has done to go out and try to achieve this objective or this task that you've given it. And if an kill occurs, all of that work is completely gone, like poof. There's no halfway point or restore that you can go back to. So kills for AI agents are extremely crucial. We want to avoid them at all costs. And there's a completely different mechanism for how it consumes memory on a system. So we basically built this dashboard um, to kind of show what that job looks like. So in the case of um, that Claude workload, it's going to go out and it's going to, run some tests here, or it's going to, go out and perform some work. So I've got this kind of, scripted for this run demo to kind of like um, replicate what that might look like, right? So what I'm going to do is I'm going to basically like run this squeeze here. And what this does is it basically starts to look like what an AI agent would do should you give it a task and it starts to go out and fill its context window. So we're looking at a dashboard here, and we'll kind of go over what each of these things actually mean. But essentially, the thing to know here is that we have a dashboard showing some metrics, some performance metrics from both a regular container as well as a Edera container that runs inside of a zone. So the key thing to know as a developer is that if you're running an Edera zone, that means that you have your own dedicated kernel instead of sharing the host kernel along with other applications, using that same shared kernel. So in this case, I kind of, you know, synthesize what it would look like if I told Claude Code to go out and, basically conduct all of these tests, right? Or to achieve this objective of finding this zero-day vulnerability in the Go standard library. Now, doing so obviously causes it to use more memory and grow that context window. So we can take a look and see what the differences are here. If we take a look on the left, this is the dedicated kernel. This is inside of the zone. And this basically means that right now we have 168 megs of memory. This is for the kernel that's only running my one application. So in Edera, every container, every pod runs inside of its own zone with its own dedicated kernel. So I can see exactly how much memory I have available to me inside of the Edera zone. In the shared kernel, you can see that I get an aggregate of the data that's available throughout the entire node. So you can see that I've got, 420 gigabits here. And this is shared across every other application that runs on the system. So if we start to, we'll come back to this dashboard here, but we'll kind of start to dive into like why having dedicated metrics or a dedicated kernel with dedicated metrics just for your application really enables you as a developer to be able to understand how your application is performing much better than the standard Kubernetes Cgroups configuration, which kind of gives you some high level statistics. You can imagine that if your application has its own dedicated Linux kernel, we get every single operating system metric that you can get out of the Linux kernel, and we can give it just for your application, right? So we can get all of these like low level pieces of metrics that we care about. For example, how much memory that we have, how much memory is cached, how much memory the kernel can free, which we'll talk about here in just a moment. And then we can, even get things like, page faults, context switches, something in the operating system called memory pressure. We get all of these low-level operating system metrics that are specific just to our application. So you can see here that the Edera metrics are in teal, and then the standard metrics are here in pink. So we have kind of an overlay here in what this dashboard looks like. And when we see, for example, this, page fault spike, for the teal, we can see that this page fault spike is specific to our application. You can see that the pink is pretty flat. So the page fault spike is only our application. So we get a tremendous amount of hyper-specific operating system metrics just for our application as a developer versus kind of the standard flat aggregate metrics that you get across a shared kernel. And that's one of the interesting things that you get when you run Edera because, isolation is great from a security perspective. We can, do things like make sure that our AI agents don't break out of the environments and take over other environments. But we also, as a developer, get our own Linux kernel with all of these, additional metrics. One of the metrics that we're going to be talking about is super crucial for how your application behaves. So let's talk about something that maybe you ran into at some point, maybe if you went to college or if you came across a white paper. There's this kind of quintessential paper called What Every Programmer Needs to Know About Memory. It was written by Ulrich Draper, I believe is his name. It seems like forever ago at this point. But the idea here is that you know, there are hierarchies of memory, right? And if you work in Kubernetes, you don't typically have to think about this because it's all kind of like under a huge layer of abstraction. But it's actually really crucial for you to be able to understand this because, under all of those abstractions is really how your application is performing. So if we take a look at this memory hierarchy, we can kind of see that we have this triangle, and at the top, we basically have the memory that is the fastest, but also the most expensive. And there's a whole bunch of really interesting reasons why it's the most expensive that go into geometry and economics and all of these other kind of whole areas that I won't get into. But the idea is that at the top you have the memory that's the fastest and the smallest, and progressively it gets slower and larger. So at the very top, you have CPU registers. This is basically like on the CPU die itself. And this is a very fast memory, right? Like it's operating as fast as the CPU. And you progressively kind of get these other caches, right? You have the L1 cache, L2 cache, L3 cache. These progressively get larger and slower. And again, there's a whole science as to why this is the case. This is typically SRAM, so this is not the type of memory that you're familiar with if you're thinking about, buying memory off the internet or something like that. This is a a different type of memory that you don't have to kind of constantly refresh with power, and it's got a bunch of additional like 3D layering of wires and things like that. It's a very fast but very expensive type of memory. Then we have main memory, which is DRAM, which is the memory that you probably are thinking of if you've ever installed like a DIMM into a server. And in this case, this is much, much, much slower than a CPU or an L0 cache. And it only gets worse from there, right? So we can go from the CPU to memory. There's a huge jump in performance, which we'll talk about here in a second. From there, we can go from memory to disk, and again, yet another huge jump in performance. So basically, the TLDR here is that we really want when our application is asking for data from memory, we really want that memory because memory is kind of this abstract concept. We want that memory to be in as fast memory as possible, right? Like ideally, if we say, hey, I need to go grab this data in memory, ideally that memory is in the CPU die. Or maybe it's in like an L0 or an L1 cache or something like that. If that's the case, then it's, that operation is gonna be really fast. If not, then we have to kind of progressively keep going down these layers. And this is called a cache miss, where basically we ask, hey, cache, do you have this? And the cache says, I don't. And then you have to kind of keep going down these layers, and each layer is effectively slower. So we'll basically go from, all of this hierarchy down, continually asking, like, can I get this memory? And the application will try to, or the operating system will try to give you this memory from the fastest, from the data from the fastest memory available. So let's take a look and see what this looks like. These are some latency comparison numbers. I don't think people look at this anymore. The latest one that I could find was from 2012, but the numbers, haven't changed dramatically. So really quick here, one thing that I want to call out is that in this data, we can see how much slower things are. So like we start at the top with an L1 cache reference, and then way at the bottom here, like we send a packet all the way from California to the Netherlands and do a round trip, packet transit. But here at the top, you can see that we're actually measuring this in nanoseconds. And if you take a look at the bottom, like there's kind of this, legend that tells us what does a nanosecond actually mean? So if we take a look, we have like 1 millisecond, and that equals like this 1,000. I forget what the US stands for. Someone on the chat probably knows and is smarter than me about computer science. And then 1,000 of those is basically a million nanoseconds, right? So if we take a look and see, like if you, to make this not just computer science trivia, if your application is asking for some data, let's see how long that data being delivered will take from each of these kind of various, areas of memory. So a layer one cache reference will take zero point 0.5 nanoseconds. Layer two cache reference will take 7 nanoseconds. Main memory reference, which means that, we're basically going to grab this from DRAM, that's going to take 100 nanoseconds. So it kind of keeps progressively getting slower, right? So we're going to go from memory to disk now. So we're going to read 4K randomly from an SSD, and that's going to take us 150,000 nanoseconds. Reading a 1 meg sequentially from an SSD is going to take 1 million nanoseconds. So this keeps on getting slower, right? So the operating system is effectively going to try and stick your memory into the fastest available cache and the fastest memory that it has to make your application perform better. Um, and if you kind of keep on going down this path, you can see that, if it's not in memory, then it has to go to disk, which is very expensive. And maybe it doesn't live in disk. Maybe you have to talk to something over the network to go and get it. And then that's, orders of magnitude slower, essentially. So with all of this said, like, why does this matter? Well, the reason why is because in the case of standard containers, what we use for monitoring memory is something called Cgroups. And Cgroups is kind of like um, the shadow on the wall for Plato's cave allegory, if you've ever been familiar with it. But the idea is that there are these people who live in a cave, and they basically see these shadows that get projected onto a wall, and they believe those shadows to be effectively reality, right? Of course, it's not reality. It's just a projection. And Cgroups is really projecting what it knows about memory and making that available to developers. So, if you're a developer and you're, sitting in this cave and you have this, shadow on the wall, that's really the only data that you have to be able to understand how much memory your application is using, whether that memory is coming from one of these faster, internal memory references, or whether it's actually coming from disk, et cetera. And how much memory is free, which we'll talk about here in a second. All of these things are kind of not what you actually expect. And they don't really go into the level of truth that you get if you don't rely on C groups, but you actually get to rely on an operating system kernel, which again, if you're running inside of a micro VM, you have your own dedicated kernel, which means that you get a real depiction. So you can see that some of these people have actually made their way out of the cave and exist up in this, non-terrestrial or at the top of this area, and they get to see the reality, right? They see birds and mountains and all that good stuff. That's really what we want. We want to enable developers with the power to have the truth, the ground truth in terms of like how their application is running, how much data and memory that their applications are using. So this kind of like asks the question, like, what if we could still have the developer ergonomics of containers where we could package up our applications and deliver them in a way that has pretty much obviously eaten the world, like everyone has moved over to containers, right? For so many good reasons. But we also got the power of VMs, which means that we have a dedicated kernel for every application that runs. Again, things like security, we get that kind of baked in, right? Like we're not going to be able to break out of this environment and compromise the shared kernel to take over every other pod. But more crucially, as a developer, we can do a lot more interesting things, such as being able to identify, how our application is performing because we have our own operating system to tell us. So let's go ahead and take a look. We can kind of go back to, I think we lost this because I've been yakking, but we can see here that we, have all of this data coming from this operating system. Now, one thing that I want to call out here is the key aspect that we all really need to care about in terms of memory is a system called mem available. So you're probably familiar with mem free. Mem free basically says like how much free memory does my application have? And that's what Cgroups tracks. So we know like, okay, a given application has 100 megs of free memory. But the reality is that free memory is unused memory. So if we go back to our diagram here, we don't want memory to be free. Effectively, we want all data to exist inside of a cache. And the reason why is because if we ever ask for that data, we want the operating system to be able to serve that data to us as fast as possible. Again, we want it ideally coming from the CPU die, if not maybe from main memory, etc. But we want that memory to exist in a cache. And all of this memory here is effectively showing you like how much data is actually in the cache. So we want data to be served from the cache. Let me go to this here so we get a little bit better view. Um, so free memory is actually not good. In fact, if an operating system has free memory, it's not really doing its job. It really should be, taking any memory that someone might request at some point and putting it in its operating system cache, because that's going to be served 100, 10 to 100 times, 1,000 times faster than if we have to go and pull that data from disk. So if we take a look at these values, we can see that all that we have for the pink value, which is standard containers, is how much memory do we have free. Now, what I really care about here is how much memory do we have that's cached. So mem available, going back to that, that's the difference between mem free and mem available is mem free tells you how much memory that your operating system genuinely is just not using. So there's like RAM that's sitting in your system that's just, filled with zeros. It's completely idle and it's not actually being in use. Mem available is actually a much more interesting aspect that we should care about. And if we kind of go back here, what I'm going to do is I'm going to release this so we have something to look at. But what mem available does is it basically tracks how much memory the kernel has available to evict to be able to give to your application. So let's think about this in terms of a real world example. Your application starts running out of memory, like here in this little graph here. So when it starts running out of memory, the first thing that the operating system does is it starts to look inside of its cache to be able to identify how much memory can I evict. For example, let's say the inside of that cache, it contains a file that maybe no one's asked for. The operating system will look at that and then realize that that's data that's sitting in this cache that we can remove from the RAM, so that we can free up memory to be able to deliver to your application. So your application at that point can basically start getting more data available from the system. It's not just whether the memory is free or not, it's how much cache do we have available and how much of that can we reclaim? How much cache can we kick out to be able to then give to our application? And you can see here that we're, in the Edera environment, we're tracking not just how much memory that we have free, but also how much memory that we have cached. And can we evict anything from that cache to be able to deliver that memory to our application when our application needs it? So there's a tremendous amount of additional observability that we can get here when we do that. So for example, here's the memory available. You can see that that took a pretty big dip when we were running that benchmark that looked like it was going out and consuming memory. We've freed that data back, which basically means that we just gave all that data back to the system, and now we have that memory free again. But crucially, the mem available is also kind of climbing back up. So that's really the key thing that I want you to remember throughout this talk is that mem available is really the crucial metric that we care about. The other, kind of data that we can look at here is, kind of just supporting data. We'll talk about some of these here in a second. But take a look at the container itself, right? Like when we ran this, you can see this huge dip here for the mem available. If you take a look at the whole node's memory, like we only got this very small dip, right? Like this is an aggregate of all of the memory that's available on the node versus like the operating system kernel that's specific to the zone, as we call it, which is the micro VM where our container is running. Um, if we start to look at some more operating system metrics, we can see where having your own dedicated kernel from a developer and observability perspective really starts to provide a ton of value. So let's bring this back into like the last 15 minutes or so. So in this case, we can see that we're also measuring minor page faults. So if you're unfamiliar, a page fault is when you go out and you say, "Hey, I would like this memory," and there's a fault. If we go back to this hierarchy here, if we try to go up to this, basically we say, "Hey, I want this memory." There's a fault if that memory doesn't exist, and we have to basically go down the hierarchy. There's, minor page faults, but the crucial one is major page faults. This is basically, I asked for this data and it doesn't exist in memory, therefore I have to go out and fetch it from disk. And disk is, 10 to 100,000 times faster, or sorry, slower than main memory. So that's a huge performance tax, and you definitely don't want a major page fault. So we can track that, for the specific kernel that your operating system is using inside of the zone. Now, the crucial thing here is that you can see that for Edera, like, there's no teal here. And the reason why is because in Kubernetes, we don't use swap, which means that you can't go to the disk and you can't rely on that. Either the data exists in memory or it doesn't. Now, minor page faults are, different. This is basically like just a standard cache miss. And we are tracking those here as well. One of the things that we're going to show here in just a second is called memory pressure. And this is a mechanism that shows, whether the kernel is blocked on being able to deliver memory or not. This is kind of an early warning indicator for kill. And again, going back to running AI agents in production, kill is the thing that you kind of drastically want to avoid, because once something gets killed, the application loses all of the work that it had just done. It's almost like if you've heard of these kind of like frontier AI labs when a GPU fails and they lose like days and hours of training time. There's a good analogy here for an kill and losing all of the state for an agent that had, spent the previous 35 minutes trying to achieve this objective. So let's go ahead and show what this looks like here. So we're going to run this pressure performance data. And what we can see here is that, this is going to not just start to consume memory, but this is also going to get to the point where we start to invoke pressure on the system, where we are asking for so much memory that the system doesn't have any available. And, basically what happens at that point is if your system doesn't have any available memory, inevitably the thing that's going to happen is it's going to kill. So we can start to look at some of this data. And we can see that, obviously the memory available, the thing that tells us the ground truth in terms of like how much memory does my application have at any given point? Can the kernel evict memory for my application to be able to continue operating? That is being tracked here. We also get to see how much cached and free memory exists here. And you can see that this cached value isn't really moving, and there's a whole reason for that. This is something called anonymous data, which basically means that this memory doesn't actually have data that exists on disk. So if this memory goes, then there's no backup to reference. And that's why we have a flat line here. Like this is all anonymous memory, which means that we can't evict that memory for our application. So we're not going to get any help there. Now, what that means is because we have basically no memory available and we don't have any available, cache to actually evict, then we're starting to experience some pressure. And you can see that we have this PSI metric instead of our zone kernel that tells us like, hey, are we starting to feel the pressure and we're not able to actually serve this memory to the system. This is an early warning indicator for an kill. And you can see here that, this is kind of rising rapidly, but also we're tracking the memory pressure here on the Edera zone as well. So we can see that, this pressure system is really driving the system, to its knees here. So you can see that we have, page faults occurring. We have lots of context switches. These are all low-level operating system metrics that you don't get with Cgroups. You only get when you have your own dedicated kernel. So I can just go ahead and release this again, and then that will basically give our application back its memory and all that good stuff. Um, okay. All right, so we said that we wanted to avoid kills. So let's talk about kills a little bit. Kills are bad. So if you're unfamiliar, when your application runs out of memory, there is a process called the reaper that comes and reaps your application. It means that it kills your application so that other applications that are running on the same shared kernel can continue to use resources without you being a noisy neighbor, without you consuming too many resources. So how does this whole process work? So in a container, a process called malloc or memory allocate, which is a system call that says, I need some memory. The kernel, in this case, is already under pressure. So we can, take a look back at our, oops, sorry about that. We can take a look back here and, if we're in this window here, like we're already under pressure, we have the memory pressure, being shown here. So effectively what that means is that we don't have any reclaimable memory. We don't have any memory that we can evict from the cache to be able to serve to our application. So this malloc call where your application is saying, I need memory allocated, cannot be satisfied. In this case, all the page cache is dirty, which means that we haven't flushed the memory out to disk. And again, this is irrelevant for Kubernetes because we don't use swap, but we're in this state where we're asking for memory and the mem available is actually zero. Like we don't have any memory available to our system. So our application's in really dire shape here. Something's going to happen and it's not going to be good. So at this point, the kernel does this thing where it basically looks at all the processes that are running inside of a C group and looks at how much memory it's using, and it kills the one with the highest score, which is actually kind of terrifying if you think about it. That means that it's not always the process that calls malloc that's going to be killed. It could be a completely unrelated process that just happens to be using more memory. And the kernel will basically kill that process to free up memory to be able to satisfy this malloc request. That causes an kill, which means that the application gets killed. You have an outage, it goes down. You need to perform incident response. You need to, hopefully this thing self-heals. But if it doesn't, if the node is out of memory, then you're in big trouble and you need to basically perform incident response, let your customers know, update the status dashboard and say that your service is down. In the case of an AI agent, again, we've asked it to go perform some very complex task, and all of that work that the agent had attempted to, do is now completely lost due to this kill. So we really want to avoid the kill. And the idea is that, if you have the data that gives you these early warning systems, for example, memory pressure, things like how much memory cache that we have, page faults, all of these low-level operating system metrics, this allows us to not fear the Reaper and not fear getting killed because we have, instead of using kind of C groups and getting this aggregate view of like how much memory that we have true ground level operating system metrics to be able to tell us exactly how much memory that we have. So here's a quick availability matrix. Like this basically tells us like, for the data that we've talked about, like does it exist in standard vanilla containers with C groups, or do you only get it if you actually have your own dedicated Linux kernel? Mem available, that's the key thing that we were talking about. This is the kernel's real ground truth in terms of like how much memory it has available to serve your application. If it needs to evict some cache, it will. If it can't evict cache, then it's not available. That crucial metric is only available inside of the operating system kernel. Cgroups does not track mem available. Therefore, you don't really know at any given point how much memory your application has. What does this mean? Well, if you think of mem-free doesn't know anything about the page cache. So it doesn't know if that page cache can be evicted. It doesn't know if that memory is actually available to your application. It just doesn't know. Reclaimable memory also doesn't exist in Cgroups. Um, there's a bunch of other kind of like low-level operating system data that either doesn't exist or it's kind of like an aggregate of node metrics and statistics that are kind of just are noise for an application developer. But if you're running inside of a microVM, you get all of these benefits, all the power of having your own dedicated operating system with all the metrics that comes along with that. If you're unfamiliar, Linux as an operating system tracks absolutely every metric that it can possibly track. It's a very comprehensive bookkeeping system of an operating system. Cgroups, on the other hand, kind of gives you aggregates and high level data. So that's pretty much it. That's all I wanted to talk about. If you're an application developer and you thought about like, why would I ever care about a hypervisor? Why would I care about having a dedicated kernel? Why would I want a micro VM? This talk was for you. I hope that this has done a decent job to let you know like why we care about having better observability for our applications. All right. Do we have any questions or anything? All right, I guess not. Okay, cool. Well, thanks so much for joining everyone and have a great day.